great to have you back. It's good to see you, and it's wonderful to have the opportunity to moderate this session. This session is the first panel session of the conference. It's on planetary habitability, Earth and beyond, and we're going to hear from 3 different scientific researchers and thinkers, and there I think will be some interesting intersections, as well as some very, very different ideas that come across, and should allow us to have some pretty interesting discussion at the end. Just a brief note on some of the odds and ends for the audience and the presenters. We're going to ask the presenters to speak for 15 to 20 minutes. I'll give an introduction right before. We'll have each of the 3 presenters go in order, and then hopefully at the end, we'll have at least 15 minutes of our hour and 15 minutes for discussion, for questions and answers. Now, if the audience can please post their questions in the Q&A function, then that way we'll be able to moderate those a little bit more effectively. And as Hava said right at the start of the conference, if we can make sure that those questions are done in a spirit of respect, dignity, and civility, which I think will be easy enough for this group to be able to do. So without further ado, I'd like to introduce our first speaker, who will be speaking on climate as a complex system, what we need to know. This presentation will be by Dr. Ariel Anbar, who's a science and education innovator exploring Earth's past and future as an inhabited world and the prospects for life beyond. Dr. Anbar is a graduate of Harvard and Caltech. He's president's professor in the ASU School of Earth and Space Exploration and the School of Molecular Sciences. And he directs Arizona State University's Center for Education through Exploration, which is reinventing digital learning through curiosity, exploration, and discovery. If you can all join me in a virtual way in welcoming Dr. Ariel Anbar.
Thank you very much. I appreciate that. And I just want to say on behalf of the Anbar family, I want to thank Roger for his very stimulating talk. My father, who is decidedly not a Marxist and not a leftist, in his middle age, when he shaped me very much as who I am, would have, I think, enjoyed that talk and would have enjoyed that presentation and would have enjoyed interacting with you, Roger. And I'm sorry he's not here to actually do that. Chava asked me to come here as a natural scientist to give a bit of an overview of what we need to know about the climate system, which I took as a charge to give a whirlwind tour of what we know as a way of framing what we don't know. Because I think that the topic of this meeting and the intersection of Judaism with climate change and environmentalism really has to do with how we deal with the things we don't know for sure. And I want to try to give you some context for that. And given that this is a conference on science and medicine, I thought to draw a little bit of analogy with the human body. And so when I talk about climate as a complex system, what I mean is that the Earth and the Earth system and the climate system as part of Earth's complex systems is a complex system, much like the human body. What is a complex system? We can argue about that. People can and have written dissertations about that. But a complex system, in one way to think about it, is one where the whole is more than the sum of its parts, which a system which is inherently very difficult to predict. And that leads to all sorts of challenges, especially when natural scientists try to engage complex systems, and especially when the consequences of the future behavior of those systems intersects with human welfare and hence with human values. And so I think it's very important at the outset of even thinking about this to adopt a mindset that says we don't want to let the perfect become the enemy of the good, which is to say we don't want to let the fact that there are things we don't understand and may not even be fully understandable and hence challenges in predicting the future, we don't want to let that become an obstacle to doing good. And there are analogies here in medicine, right? We have all sorts of theories of disease, right? Many of which, if you scratch the surface of them, are very weak theories from a pure science standpoint, right? There's a lot we don't know. And yet that doesn't prevent us from acting based on what we think we understand about human disease in order to help people get better when they have disease or help people avoid disease, right? We don't let the perfect become the enemy of the good when it comes to the complex system of the human body. And we need to adopt a bit of that mindset as well when it comes to, or a lot of that mindset when it comes to managing Earth's future as best we can. So a little bit about what we know, or maybe too much about what we already know, but this was the charge I feel I was given. So I'm going to march through some figures here with sort of bullet points on the left if figures sort of make your eyes glaze over. And I'm addressing some common skeptic arguments a little bit here. And I just want to drive things home in case you are wondering about certain things. So first of all, global average temperature which is a construct, but it's a useful one. Global average temperature is definitely rising. It's been beaten on and chewed on, and I'm showing here in particular data from a project called the Berkeley Earth Project, which was put together by a esteemed physicist who was actually quite skeptical of global climate temperature records, and in a kind of celebrated way, but he took a very objective look at it and came basically to the same conclusion that consensus science has come to, which is that global temperature has been rising for the last 150 years in a very clear and concerted way that we can measure. Why are my slides not advancing the way they should? Sorry, here we go. And this temperature increase is unusual in size and speed. This is a very famous and controversial figure called the hockey stick figure, called that because of the upturn in the last 150 years. And in this figure, we're going over looking at the last 1,000 years of the Earth's temperature record. This was a very controversial data set when it was first presented, because there's a lot of argument about how we're combining direct measurements that are made today with historical measurements, with reconstructions from all sorts of proxies in the geologic record and other records, all of which have uncertainties. Lots of argument, lots of drama, but the upshot of this is that this figure still stands as showing without much doubt that what's happening in the last 150 years is certainly unprecedented in the last 1,000 years. It's now emerging above the noise, and we can reconstruct records going further back that show that indeed the Earth has been as warm as it is now at various times in its past, and so on. But what's happening now is certainly an unusual event that we find a few parallels for in the geologic record, but not very many. So it's unusual in the magnitude of temperature change, and it's unusual in the speed. And it's very hard to argue against that at this point. We also know that CO2, the carbon dioxide, which is the critical gas that most of us, as we'll talk about in a second, think is shaping this change of temperature. We know that CO2 in the atmosphere is rising. We have exquisite records from the last 60, 70 years or so, like this one here. So exquisite, these are direct measurements of carbon dioxide, so exquisite that we can actually see these little up and down seasonal variations. This is essentially the breathing of the biosphere in North America, right? You're seeing the consequences of the expansion of biological activity during springtime, which draws down CO2 a little bit, and the contraction in wintertime, which causes CO2 to go up a little bit. So we can even see the breathing of the biosphere superimposed on this very persistent record going upwards of carbon dioxide in the atmosphere since the late 1950s. And we have other ways of trying to reconstruct carbon dioxide over time, going further back, going earlier, looking at ice cores, and we have other ways as well of inferring or even almost directly measuring what carbon dioxide in the atmosphere was in the past. And we can see that what's been going on in the last century or so, last 150 years or so, with respect to carbon dioxide, is also unusual in size and in speed, very analogous to what we see with temperature. And again, this is a very hard thing to argue about. And as a geochemist who studies this sort of stuff, I would say it's not disputable. It's also not disputable that we are putting lots of carbon dioxide in the atmosphere. And in political debates about this, we see a lot of strange statements made sometimes. This is showing you reconstruction. We have good historical records. We have good industrial records of fossil fuel use. And we have pretty good reconstructions at this point of where all that carbon goes. And so in this diagram here on the right, you can see this huge wedge here. I'm probably colorblind, so I'm not sure what color this is. This huge wedge here, this is carbon dioxide emissions from fossil fuel burning in industry. And you can see here, this is the flux of carbon dioxide into the atmosphere. There is plenty of fossil fuel burning to account for the accumulated carbon that we see in the atmosphere. And what doesn't go into the atmosphere goes into the oceans and into some other areas, other parts of the system. So we know that we have been putting carbon dioxide into the atmosphere, and we know we have injected more than enough carbon dioxide to account for the carbon dioxide that we observe has increased in the atmosphere. It all hangs together. And I'm an isotope geochemist in particular. I study in particular the chemical composition, the different kind of isotopes of elements and what we can infer from that in the geologic record. So I just have to show this figure. I realize that this is kind of a scientist nerd kind of figure, and I'm not going to walk through it in any kind of detail except to say that the kind of carbon that is in that CO2 in the atmosphere is distinctive. It has a fingerprint that is a fingerprint of carbon that's coming from the biosphere, which is what you would expect if you're burning fossil fuels. Fossil fuels are the remains of dead organisms. It's yesterday's biosphere being stuck into the atmosphere today. And so when you see here carbon dioxide going up over the last 150 years sharply, and you see this mirror image of this delta C13, this is the isotope composition, this is the fingerprint of carbon in that CO2 shifting in concert, it's impossible for me, very hard for me as a geoscientist to look at that and come up with explanations for that parallelism of the CO2 rise and this shift in the fingerprint that does not involve mobilizing carbon dioxide, carbon from the dead biosphere into the atmosphere. And there are other additional fingerprints we could look at that just augment this story. And there are none that cut against it. So temperature is rising, CO2 is rising. We're responsible for that CO2 rise. These are facts that are not really contestable in a reasonable way. And then we have a theory. Right? We have a theory that is not too complicated. It's complicated. In this diagram here, you can see the things that have to be turned into math to make this theory work. And so there's a lot of arrows here of what's going on with energy as it comes in from the sun and how it leaves. And it gets complex when you get into the details of it, but it's not terribly complex. It's beyond the freshman physics level, but not far beyond. And the basic math and physics of how you relate sunlight coming in, energy going out, carbon dioxide in the atmosphere, and the consequences for temperature at the surface have been understood for a long time. Right, so the basic theory of this is not exotic, is not weird. It's very straightforward for those trained to study it. And we know that it naturally occurs and is essential for planetary habitability. The natural greenhouse effect is essential for planetary habitability. Without the natural greenhouse effect, the natural amount of CO2 that's in Earth's atmosphere, which helps provide warming along with water vapor and other gases. Without that, the Earth would be a frozen ice ball with a global average temperature of about 0 degrees Fahrenheit, so well below freezing. So this is sort of foundational to our understanding of planetary habitability, which is the theme of this session, and which I think Howard will get to in the next talk a little bit. It's basic to our understanding of planetary habitability that the greenhouse effect keeps the Earth from being frozen. And if we look at Mars, which is colder, and Venus, which is warmer, to some extent, those differences are due to the distance from the sun, but that doesn't explain everything. And in fact, doesn't explain most of it. Most of the differences in temperature between the planets that are similar to Earth have to do with differences in the atmosphere composition interpreted through the greenhouse effect. And so this is just fundamental in planetary habitability. Where it gets complex and where there becomes a room for argument and debate is that climate models, global climate models, that try to provide the kind of information, kind of predictions about global temperature that policymakers want on a short time frame, what's happening next decade, what's happening at the end of the century, and where we're then trying to predict differences of a few degrees, that becomes tricky. Those models are complex. Those models have to take into account all the complex feedbacks you see here in this, all the physical processes and chemical and biological processes too, that go on at the Earth's surface. And that creates a lot of challenge to understanding. And frankly, because it's so complex, because there's so many feedbacks that are hard to figure out, even the fundamental understandability of the system is challenging, right? That's the hallmark of a complex system. Even so, our understanding is good enough that when we look at what these models predict, if anything, they have predicted more warming than we have seen. So this is a recent assessment of a very famous paper from 1988 from Hansen, 1988, that compares real observations of temperature to predictions that were in that paper. That paper was written in 1988, so this was retrospective, and then going this way was prospective. And the big challenge, the big argument around this paper has not been that it predicted warming and the planet didn't warm. The argument is over a few fractions of a degree, and whether or not, why did the model at that time overshoot? And we think we understand why it overshot, and so current climate models compensate for that. And so when we predict warming going forward, we have learned over the last 30 years a thing or two. So the models improve over time as we compare reality to observations. So the models are complex, but we think, I think a fair assessment of them is we understand them well enough to be able to make certain kinds of forecasts. We can look also at what's now is actually going on over the last, especially the last 30 years, where we have really good data. And we see things like the poles getting warmer faster than the mid latitudes. That's a hallmark of greenhouse warming. It's a fingerprint of greenhouse warming. You would not predict that necessarily from other explanations of the warming, but it fits the greenhouse theory, or it's predicted by the greenhouse theory. So you can see here the darker colors in the North Pole are evidence that are a representation of the fact that data show that the Arctic has warmed much faster since 1951 than the rest of the planet. We can look at other fingerprints as well. We can look at, compare what's happening in the lower part of the atmosphere, the troposphere, to the upper part of the atmosphere, the stratosphere. And greenhouse theory, unlike certain other explanations for temperature change, predicts that as the lower part of the atmosphere warms, the upper part of the atmosphere, the stratosphere, should cool. And that's in fact exactly what we see. And we can argue about the details, but it seems pretty clear that the reason for this difference, it's increasingly clear that the reason for this difference between the troposphere and the stratosphere is because the warming that's happening is due to carbon dioxide and other greenhouse gases affecting the climate. So as we look forward, as we try to project forward with our models that are complex, trying to predict a complex system that's difficult to predict, we can make some statements that are pretty strong that then come to the point of this meeting of the intersection of Judaism and climate. So this is showing, this figure here is showing future projections of temperature for different scenarios. Here you can see the observations, the historical observations, and then here's going forward. Here are different scenarios, some of which show temperature sort of leveling off at 2.5 degrees or so warmer than today. Here you have temperature getting much warmer than today. You have uncertainties. These big fuzzy bars, right, represent the uncertainties in the models for these different scenarios. What are the differences in these scenarios? What's the cause of the difference in these scenarios? Well, these are different scenarios of what humans do in the future. Right? These scenarios are derived from making different assumptions about what we will do in terms of fossil fuel use and hence carbon dioxide emissions, as well as other sources of greenhouse gases in the coming century. And the point to take away from this is that this figure is that the difference between these scenarios, which depend on what we do, are much bigger than the variations from natural variability and the sort of uncertainties that are in the system, at least the known uncertainties, the ones that we understand well enough to put inside our models. What we do increasingly is what is going to shape the future. Future human decisions about carbon dioxide emissions will have more of an effect on the atmosphere, on temperature, than natural variability, given everything that we understand and know at this time. And I just want to pause. That's really important, because there are a lot of arguments over, could this happen? Could that happen? When you look at the models and when you plug in what we know, increasingly it's our actions that are going to shape more and more what happens in the future. And that's true not just of climate and carbon dioxide. This gets into kind of what Roger was talking about. I like to look at this because I'm a natural scientist. This is looking at total energy use through time, and this blue curve that's buried here is the actual data for energy use by human civilization, which has been increasing at this sort of exponential rate, more or less mirroring population growth. We are now using energy at a rate that is comparable to about 10% of the energy used by the entire global biosphere, right? So all the plants, everything you look outside that's capturing sunlight every year and flowering, right, and giving then rise to the rest of the biosphere, that amount of energy that the natural biosphere is capturing every year and pumping into the Earth's environment, we are now at about 10% of that, mostly heavily driven by fossil fuels, by burning ancient biosphere. And it's always dangerous to take an exponential curve and just willy-nilly extrapolate it forward, but let's do it for fun and for some sobering thoughts. If we extrapolate that forward, we find that not that long in the future, about a century from now, we end up, even crossing that global biosphere curve. Now, I'm not saying that that's a prediction. This, putting an exponential curve like this and just taking it forward is in some ways a little silly, but in some ways it's not, because it's hard to imagine that we will not continue to want to increase our use of energy even as population levels off in the future, we want to do more and more things. Use of energy enables us to live at a higher standard of living. So there's going to be a pressure to continually use more energy from some source. And even if we get off of fossil fuels, which I certainly hope we do, and find alternative ways to generate energy so we don't create a climate crisis, we will create other crises. Because you cannot use energy at the level of even 10% of the global biosphere, let alone start to rival it at some point in the future. Maybe it's 100 years, maybe it's 200 years, maybe it's 500 years. And maybe in 100 years, we're only at 25%. Okay, whatever. You can't use energy at that scale to do stuff at Earth's surface and not have an impact on the environment. Because what are you using that energy for? You're using it to do stuff, to build buildings, whatever you're doing. You're having an impact. And that impact is going to have consequences for the natural pre-human system. And so I see climate change as just a leading indicator of what's coming. And I think Roger alluded, or more than alluded to that as well. We can focus on climate, but it's just one small piece of a much bigger picture. And so, when we argue about whether, droughts in Australia a couple of years ago is a consequence of climate change, or whether the freezing weather in Texas earlier this month was a consequence of destabilization of the climate system because of climate change or not, all of these are all important arguments to have. But in some sense, they are kind of missing the point. They're looking at important details that miss the bigger picture. To paraphrase Hillel, right? What's the essence of Judaism? Don't do to others what's hateful to you. All the rest is commentary. Well, a lot of this is commentary, right? Because the big picture is that Earth's future is in human hands. And we need to figure out how we're going to deal with that. So the arguments over particular weather events and whether they are a fingerprint of climate change are important, but what's more important is to understand how we're going to have those arguments in that discourse and how we're going to deal with the uncertainty, which is inevitable around many of those specific particular arguments. Right, the Earth's future is increasingly in human hands. Geoscientists like me are starting to call the era that we live in the Anthropocene, the age of humans, because our impact is becoming difficult or impossible to deny. And as we look forward, it just increases. So how are we going to deal with risk and uncertainty about what's going on? And so there are all sorts of dysfunctions, right? I mean, there's denial, there's despair, there's delusion. Those of you who are physicians probably see all of this in your practice when dealing with difficult futures. And we need to figure out how to navigate, right, and avoid these pitfalls if we're going to try to figure out to construct a positive future. I'm inherently an optimist, so I think there has to be a way. But whether you're an optimist or not, denial is obviously not a path. Despair is not a path, and delusion is not a path. What I hope is that we go into a future that is one of sort of deliberate management and design the best we can, as we do in other spheres of our life, our own bodies, our health. We try to manage our health. I think we need to think about trying to manage our planetary health. And so as we enter into this Anthropocene, right, increasingly, the message is, the take-home message to wrap this up is that the future is going to depend on human actions, and hence that means it's going to depend on human values and how we decide to manifest them in the world. So as a geoscientist who studies the natural history of the planet, and I try to think about what the natural future history of the planet is, I can no longer divorce human values and human decision-making, human tolerance for risk and how we deal with that, how we deal with uncertainty. I can't extract that. I can't think about Earth's future without considering all that and asking questions like, well, what are human beings going to actually do? And that brings us then to Judaism and other value systems that are going to shape what our response will be. So I will stop there, except to say that I just want to say a couple words to set up the next presentation, Howard's presentation, which is going to take us off this planet, to say that this realization that the planet's future depends increasingly on humans and what we do leads many of us to be very interested in the possibility that there could be life elsewhere, intelligent life elsewhere, that might have figured this out. Do we have anything to learn by thinking about what could be out there, and by even looking for evidence of intelligent life elsewhere? And that motivates a whole field of study in a kind of subtle way. It's not usually said, but it's this questions about Earth's future, I think, that really motivate this field of astrobiology that leads us to ask, are we alone or not? And if we are not, what does that teach us? And if we are, what does that teach us? And so I'll stop there. I'm glad to take questions on my part and hopefully to set up Howard a little bit. Thanks.
Thank you very much. I think what we'll be doing is working through each of the three presentations one after the other so that we can have a good solid piece of time for the questions at the end. Thank you also for setting up Howard Smith's talk. I just briefly like to introduce Howard Smith. Dr. Smith is the senior astrophysicist at the Harvard-Smithsonian Center for Astrophysics, as well as a lecturer in the Harvard Astronomy Department. He studies star formation in the universe with space and ground-based telescopes, as well as supermassive black hole activity and cosmic infrared phenomena. He writes and lectures widely on science and religion, and is the author of the book, Let There Be Light, Modern Cosmology and Kabbalah, a new conversation between science and religion. You all will please welcome Dr. Smith and his presentation, Alone in the Universe, Why We and Our Planet Earth Are Exceptional. Dr. Smith.
Thank you very much. You can hear me okay?
Yes, we can.
Yeah, great. Thank you. Thank you to conference organizers, and thank you to everyone for coming, and thank you for this opportunity to explain to you why I think we are exceptional and why that's important. Right, and here we are. Here we are. This is the distant universe seen from the Hubble Space Telescope. And everything that you see here, except for one star, is a galaxy, a collection of hundreds of billions of stars. The universe is 13.8 billion years old, and the light from the most distant of the galaxies in this image, the red ones, that light has been en route to us for over 10 billion years. And a reminder, nothing travels faster than light, 186,000 miles a second, and a light year is the distance that light travels in a year. And the insert at the bottom, that's a nearby galaxy, somewhat similar to our own Milky Way, and our sun with its planets roughly located where the arrow points. The universe is expanding, and because of the expansion of the universe, these red galaxies are today more than 80 billion light years away from us. And if an advanced alien civilization in such a galaxy were today to say, oh, look, we found a planet called Earth in a galaxy called the Milky Way, and in another 10 billion years, our computers tell us a civilization will develop there. So let's send them a laser message. Well, that message would not reach us, not in 80 billion years, and not ever, even if the universe lasts forever. Because the universe is not only expanding, it's accelerating and dragging the signal with it. The universe is vast. Its stars, its planets, black holes, nebulae, other constituents, innumerable. But they're also very far away, so far that for all practical purposes, we are alone. This is an artist's painting of the Milky Way, our galaxy, and our location on it is marked. And even with our own galaxy, there are hundreds of billions of stars stretching across more than 100,000 light years. Nowhere in the universe is there anything as complex as life. Life is by far the most intricate, complex entity that we know of in the universe. We may be small in size, but nothing comes close to humanity and life in complexity. And it took 13 billion years and immense resources for complex life to emerge. So consider black holes on the right. A black hole is completely described by three numbers: its mass, its spin, and charge. If you know that, you know everything. The other image is a human zygote. To be alone means to have no one to talk to. Maybe there are bacteria on Mars, or even beneath the moon's ice, but we're still alone. And proof, if we find bacteria, that even 5 billion years after the solar system was born, only intelligent beings exist on the Earth. The idea that other Earths and alien life may exist around in the stars is ancient. Here's Democritus, innumerable worlds of different sizes. Here's Giordano Bruno, burned at the stake in 1600 for heresies like thinking there was life on other stars. You know, the Bible hints at life on the stars, and the Talmud and commentators discuss it without much incredulity. But today we know for the first time how vast space really is. How many are its stars? And I'm going to tell you about new discoveries, thousands of planets. So how should we react? Here are two typical reactions. Carl Sagan's. We find that we live on an insignificant planet of a humdrum star lost in a galaxy far away. And Stephen Hawking, we are so insignificant, I can't believe the whole universe exists for our benefit. So this front and center, it seems to me, is the subtext for our conference on climate change and the issue at hand. Because if we are insignificant, if we are just one of trillions of cosmic species, then does climate change really matter all that much? Astronomers have discovered so far, just in the past few decades, over 4,000 planets around other stars, so-called exoplanets. And this video orrery gives you a rough sense of their diversity and multiplicity. The sizes and colors reflect the sizes and temperatures of the planets, and the periods are reflected in their orbiting. And I can play this for you. Here's the solar system for comparison, and you can see the wide variety of types of exoplanets that exist. You can imagine how difficult it is to spot an exoplanet, and let me tell you briefly 5 common methods used to detect them. So the first method, and the most common, is so-called transit method. In that method, the light of a star is blocked by a planet as it orbits. And when the planet blocks the star, the light dims, and after many, many orbits, astronomers build up a signal showing the depth of that absorption and infer the presence of the planet. And there are 4 other methods. One is direct imaging, not very common, but very easy to understand. Here the star is blocked out with a mask, and it enables telescopes to see faintly the presence of a planet and to follow it over the years so that you can track its orbit. There's the wobbling method. As the unseen planet orbits its star, it pulls the star back and forth slightly, and that wobble can be detected in inferring the presence of the planet. A little more complicated method is the gravitational microlensing, where the star passes in front of a distant background star, and the gravity of the star in front acts as a lens, a gravitational lens, to make the background star light brighter. If that star has an exoplanet orbiting it, that planet's gravity also will make that background star a bit brighter. So this is an unusual but successful way to detect exoplanets. And the last one is astrometry. As the planet orbits the star just moves back and forth, and its position gives it away. Today, as I mentioned, the number of confirmed exoplanets is about 4,300, and thousands more are hypothetical and remain to be confirmed. Well, today's discussion is about the Earth. Is the Earth commonplace, or is it rare? Is life rare? Well, we think life anywhere would require liquid water. And so really the search is on for exoplanets where liquid water could exist on the surface. Temperature is the key factor, and astronomers define the habitable zone, shown here, as the region around a star where the temperature would allow liquid water on the surface. Not too cold, where it would be icy, not too hot, where it would evaporate. And here is a plot, a little bit complicated, showing some of the results. It plots this mass of the star, one solar mass here, and the distance from the star, 1 astronomical unit. So here's the Earth up here, and it shows the habitable zone and detected, measured exoplanets. And you can see that there are many planets in this habitable zone of liquid water. And of course, many more of them not in the habitable zone. And even those within the habitable zone are not necessarily Earth-like. It turns out that exoplanets are surprisingly, fantastically diverse, much more than we had expected. And most of the diversity that we see makes them hostile to life. This plot shows the planet size versus the planet mass, and roughly groups the detected exoplanets into 4 categories. Ones like the Earth, shown here, terrestrial-like, Earth and Venus are here. One of the categories, super-Earths and mini-Neptunes, we don't even have one of these category in our own solar system, but they're relatively common in the universe. So remember, we've never directly resolved an exoplanet image. The sizes are inferred indirectly from other properties like the width of the transit curve, but that doesn't prevent the media from inundating us with artistic concepts about what they might be. But that's all that they are, artists' ideas. So these discoveries are amazing achievements. But the existence of exoplanets is not surprising at all. Thoughtful people have always imagined that stars have planets. The new results, though, enable us to study the range of planet types in detail and to model how they form. And the surprise has been that the variety of planet types is vastly greater than anything that had been proposed before. So here's the solar system, for example. 3 planets in the solar system, Earth, Venus, Earth, and Mars, are in the habitable zone. But there's intelligent life on only 1, and maybe no other life of any kind on anywhere else either. So what does it mean to be alone? It means in this vast universe to have no one to talk with or learn from or teach, no one to communicate with. Are there alien civilizations on these galaxies? Maybe, but we'll probably never know because they're too far away. To be alone, for all intents and purposes, means to be without any communication, or even the knowledge that a signal is coming for a very long time. So how long should we wait for such a signal? 10 billion years? Forever? So my choice, for practical reasons, is 100 human generations, a long time, 2,500 years, time enough to hear and reply to all the aliens closer to us than 1,250 light years. And that's the volume in this circle surrounding us in our Milky Way. So what are the chances for life to be present in this volume? The Drake equation is an accounting scheme that tracks the probability of 5 phenomena thought necessary for life: the number of suitable stars, the number of suitable planets around a suitable star, and that's really the new information that we have from the detection of exoplanets, and then 3 biological terms: the probability that life develops on a suitable planet, that it evolves to become intelligent, and that the lifetime of a civilization compared to the lifetime of a star is long, because if the civilization does not last very long, then it won't be there now today. Will we find aliens? Well, here's what Stephen Jay Gould says about one of the biological terms. Homo sapiens are a tiny twig on an improbable branch of a contingent limb on a fortunate tree. Very unlikely. Fine, it's unlikely, but will we ever know? In 100 generations, light can travel the volume enclosed in this circle. The recent Gaia space mission has counted the stars in this neighborhood. There are 35,171,000 stars, plus or minus a few percent, in this volume, and about a few 100,000 are G-type stars like our sun. So the chances may be slight that any in this volume host intelligent life. And after 100 generations of waiting, we will probably still be waiting. So what do you think is the chance that life will appear on a planet with water, evolve, and survive as a civilization? Is it 1 in a billion chance? Well, then we're probably alone. The misanthropic principle is the idea that the multiplicity of possible environments in this perfect cosmos are so varied, uncooperative, and hostile, either always or at some time during the roughly 4 billion years intelligent life needs to emerge, that it's unlikely for intelligent civilizations to form and thrive. And for all practical purposes, we are probably alone. But that doesn't stop people from wishing. People like to wish. Here's astronomer Jerome Lalande, the senior director of the Paris Observatory in the 18th century. Here's how he put it. Is it rational to suppose the existence of living and thinking beings confined to the earth from what is such a privilege derived but the groveling minds of persons who can never rise above the object of their immediate sensation? And more recently, here's Percival Lowell, director of the Lowell Observatory, writing in his book on Martian canals. From all we have learned of its constitution on the one hand, or its distribution on the other, we know life to be as inevitable a phase of planetary evolution as is quartz or feldspar or nitrogenous soil. Each and all of them are only manifestations of chemical affinity. No one believes this today. Nobody believes it. And all school children whose minds are neither groveling nor privileged, they all know there are no canals on Mars, and there are no Martians either. This is the problem. Great philosophers and scientists of the past, filled with hubris that they know more than they do, make a big assumption. They assume we are commonplace. They assume we must be, since we understand the universe and its laws, and these are the result of random accidents. Theologians, in contrast, assume that the earth and its inhabitants are special. But both are assumptions. They're derived from belief, not from facts. And the truth is somewhere in between. So I want to leave you with 3 takeaways from 50 years of astrophysical discovery. The first is that planets are vastly more varied than we had imagined, and also more hostile to life. The second is the universe is so large that nearly all of it is inaccessible to us. We won't ever know if life exists in these distant realms. The cosmic neighborhood that is accessible to us in 100 generations, so a long time, but still accessible, has fewer than 1 million solar-type stars. And if the chances of life forming, evolving, and lasting out of a warm ocean are 1 in 1 million, then we may not be unique in the cosmos, we don't know, but we are probably alone. Here we are again in our cosmic neighborhood. And what do we make of this conclusion? We're not cosmically irrelevant, insignificant, or common. And to recognize this is to have a renewed appreciation for our good fortune, and to acknowledge that the earth is precious and deserves supreme respect. Modern discoveries in astronomy and physics highlight the many blessings we enjoy, and with these blessings come responsibilities. We must care for our planet and all life with renewed dedication. The earth and humanity, if not unique, are very rare. No aliens will come to help us. I am the co-author with Art Green and Deborah Band of a new illustrated translation and science commentary of The Secrets of Creation, classic Kabbalistic treatise by Rabbi Meir Ibn Gabbai, born in Spain in 1481, about 100 years before Giordano Bruno. And he writes, "Those above have a need for those below, for their preservation and their arrangement." Here's Ibn Gabbai's response to Stephen Hawking's remark. Yes, the entire universe does exist for our benefit. We are by far the most complex entities in the cosmos. It took 13 billion years to make us, and vast resources are needed to produce the unusual, complex, intelligent, self-aware life through the processes of natural evolution. And more than that, what we do matters. Of course it does. Everyone understands that actions have consequences. Climate deniers as well as environmental activists know this. Spiritual awareness is not needed to call for action to protect the earth. For the secular, the Torah's call to protect the earth is not more compelling than the Sierra Club's. But Ibn Gabbai and Kabbalah in general raise the stakes. Our actions have cosmic ethical consequences that skeptics do not acknowledge. Are we unique? We don't know. It's not likely that we will know, one way or the other, for eons, if ever, because the cosmos is big and we are rare. But if thinking, self-aware, intelligent beings are the pinnacle of cosmic evolution, then the entire universe exists for them and for us. In return, by caring for the earth, we also care for the universe and its precious life. But perhaps this task is too messianic. Fixing climate change, caring for others, not destroying ourselves with bombs. This work is too hard. And so let me leave you with a quote from the first century Tana Rabbi Tarfon, who used to say, "It's not incumbent on you to finish the work, but neither are you free to refrain from doing it." Thank you.
Thank you very much. That was a wonderfully complimentary presentation from our first presentation. I'd like to move us to our third presentation entitled Climate Science and Public Policy, The Challenge of Science is an Ongoing Process. It will be delivered by Peter Rez of Arizona State University. Dr. Rez's earliest work is on elastic and inelastic scattering in electron microscopy. He calculated the ionization cross sections used for quantitative electron loss spectroscopy and worked on interpretations of EELS fine structure. This led to other applications of density, functional theory, and material science. He has an interest in biomineralization, both in kidney stone formation and the mechanisms behind the formation of amorphous calcium carbonate. And he has been very, very active in physics as it affects society, in particular radiation from airport body scanners and energy policy. Dr. Rez, please.
Can you see my slides?
Not yet.
Oh, right. I have to get my wife to fix that out. First, let me just say that I'd like to thank Chava for letting me speak. God, he's going to be in the Zoom.
Can they see him now?
No, they probably can't.
No, we can't yet.
It's going to be in the Zoom.
Wait. Share screen. There we go. Right there.
And as they're continuing that, I'd like to remind participants, if they have questions, to use the question and answer function. I know a number of the speakers are already answering some of the more concrete questions through that function, and we'll also be combining them at the end for a few questions and answers for the entire group.
Can you see the slides now?
Yes, we can.
Good, thank you. All the time I hear, I follow the science. I believe in science. I believe that humans cause global warming, global climate change. But what does belief have to do with it? Isn't belief something more associated with religion? As in, I believe the Torah was handed down to Moshe on Mount Sinai. I believe Jesus was born from a virgin and died for our sins and then was resurrected, and so on. Although one could say that Judaism, compared to other religions, is probably a bit light on the belief side. Belief is a foundational assertion, something that really cannot be questioned. It's, if you like, the cornerstone, a Rosh Pinah, on which a massive intellectual edifice is built. So does science have beliefs? Well, I suppose in a sense it does. I think what the main one is that we can understand the world and the universe as a whole, as Howard Smith was telling us, using logical reasoning. But that in itself is not enough. The ancient Greeks were good on the logical reasoning. You could look at the Talmud as a wonderful application of logical reasoning. We start with the premise, God is perfect. And so there has to be total self-consistency among those minutiae of rules and regulations. So there's something important that's missing, which we really have to add to just logical reasoning, and that is agreement with experiment or observation. So this is a view of how science proceeds. We start with a hypothesis. We then model the consequences. Preferably that should be quantitative. Why? Mathematics is just a symbolic language which enforces the rules of quantitative or logical reasoning. We then compare the consequences of that prediction with observation. If it agrees, great, we have a scientific conclusion, or maybe we could call it a fact. If it doesn't, maybe it's just a little bit off. We perturb things a bit, we change things a bit, we modify the hypothesis, and we go around the loop again. And if it's totally off, well, you just have to chuck it out. Feynman summed this up beautifully. I feel a certain affinity with Feynman. I mean, yes, he's Jewish, we share the same birth date, and he had great sense of humor. He was a fun-loving person, very irreverent, and if you don't believe me, just read his accounts of his service on the Challenger Commission and his unlikely friendship with an Air Force general. Feynman said this: first you guess, don't laugh, this is the most important step. Then you compute the consequences, compare the consequences to experience. If it disagrees with experience, the guess is wrong. In that simple statement is the key to science. It doesn't matter how beautiful your guess is or how smart you are. I could add how many people agree with you, what your position is or anything. If it disagrees with experience, it's wrong. That's all there is to it. I suppose in a sense, this accords with, I mean, Professor Gottlieb mentioned the idea of science is as prophets. Well, I don't think I'm a prophet, but in a sense, the test for whether a prophet is for real or whether it's a fake prophet in Parshat Shofatim says if it actually happens, then they're real, and if it doesn't, then they're fake. So let's examine anthropogenic climate change within this framework. And Ariel Anbar has already been for a lot of it. There's the sun out there. It's a nice hot body. It radiates in the visible. It's a long way away. It heats the Earth. The Earth warms up to an average temperature about 15 Celsius to 85 Kelvin. It radiates back in the infrared. There are various gases in the atmosphere that absorb that infrared and then re-radiate it. Half goes back into space, and the other half goes down to the Earth. So what's there that's doing all this absorption and re-radiation? Well, there are three main things. There's water, carbon dioxide, and ozone. We can know this by just looking at a spectrum. And here we have this spectrum. Now, I said that the Earth was around 285 degrees K, so you'd expect us to follow that upper red curve. Well, it's depressed from that. That's mainly the influence of water vapor. You can especially see the water vapor here and here. What about the carbon dioxide? That's that big dip in the middle. Well, that's a worry, isn't it? Because as Ariel Anbar told us, the carbon dioxide in the atmosphere is increasing. Where I disagree with him is, in fact, most of that increase has actually happened since about 1960, 1970, not this 150 years. And superimposed on this gradual increase, about 2 parts per million per year, there's an 8 part per million fluctuation from natural vegetation growing and then decaying in the fall, which Ariel Anbar mentioned. But this looks really bad, doesn't it? That massive dip there. But you know something? That was there when Moshe went up Mount Sinai, when Maimonides wrote the Guide for the Perplexed. It's always been there. It's the technical term is that the carbon dioxide line is saturated. So the differences from this extra carbon dioxide are only in the boundaries, in the wings. They broaden it a bit. And you can see that. This is a calculation showing what would happen if you go from about 300 parts per million, where it was about 100 years ago, to 600 parts per million, which is way more than we have right now. It's just these little changes in these boundary regions. And to calculate that, you have to worry about all sorts of obscure combinations of rotational transitions of the molecule and bending motions. It's all in a big database called HyTran. So how do we predict what's happening? Well, we've got to quantify that. And let's start with the radiation coming in from the sun. It's 1,400 watts per square meter. Well, half the time it's night, so we'll cut that to 700. The sun angle is changing during the day. Cut it by 2/pi, 450 watts per square meter. What's this extra contribution from the carbon dioxide in the atmosphere? That's called the top of the atmosphere radiation forcing. That's how it goes into the models. It's about 1 to 2 watts per square meter. The exact number, there's quite a bit of uncertainty on the exact number, but that's the sort of numbers that I talked about. So it's about 1%. So the point I want to make is it's small compared to other things going on. And that's where things get difficult, because how do you model these very complex systems that Ariel Anbar talked about? So I'm going to go for a little digression here. Why are we meeting like this? Why aren't we all in a room together? Well, we all know it's the COVID pandemic. Modeling the climate is hard. There's a lot of things going on. There's the atmosphere, the oceans, the cryosphere, what's going on the land masses. As Ariel said, it's a very complex system. Epidemic modeling, by contrast, is really easy. You basically, in the simple models, you basically consider 3 groups. There's what's called the susceptible, those who can get the disease, the infected, those who can pass it on to the susceptible, and the recovered, those who have been infected and then are no longer, the disease has run its course, they're no longer infectious, they either survive or they die. They're recovered includes both of them. It's all summarized in these 3 equations. But the key things in those equations are these parameters, beta and gamma. You probably all heard about R, this R factor for COVID. Well, R is a ratio of beta to gamma, basically. It's a disease growing faster than it's diminishing. Well, it took me about an hour to write code to implement these equations and debug it. I'm not alone. Many other people have done it in about the same time. You get out results like this. The disease peaks and then drops off with a certain time period, which you can match to observation. The integrated number of cases climbs up and plateaus. And guess what? Yes, it even agrees with observation. This is for Australia, where we just had this one big peak. At least in the early days, I could do the same for India. But predicting the absolute numbers who are going to get the disease, the absolute numbers who are going to be hospitalized, the absolute numbers who are going to die, I was way off, and so is everybody else. from all those fancy models you hear about, like the IHME model from University of Washington, from the Ferguson model in the UK, which was very badly off. I mean, the numbers were just wildly, wildly wrong. And this tells you something which is very common in theoretical modeling. That's what I do for a living, mathematical modeling. You can get general trends right, but you'll often be way wrong on the absolute size of the effect. Let me return to CO2-induced climate change. It's absolutely true that CO2 levels have been increasing. Most of the increase has happened in the last 50 to 60 years. You know, it's said some time ago it was 285 parts per million. At the end of the Second World War, it was 310 parts per million. Now it's just over 400. Notice these temperature changes are quite large, you know, that compared to other things going on. So I would say that you're really only noticing these temperature changes now. Well, noticing might be the wrong word. We're talking about a change of about 0.7, 0.8 of a degree. However, as I was saying, models can be useful in giving you qualitative effects, so telling you what are the signatures of this particular possible cause. And as Ariel Anbar mentioned, a key signature of CO2-induced warming is a big difference between the tropical regions and the polar regions. In fact, all the models from the earliest to the latest all say that the tropical regions should be largely unaffected. So I kind of get rather tired about this talk about how people in the equatorial belt in poor countries are going to bear the brunt of it. They're not. It's in the polar regions that the big changes occur. The other thing that Ariel mentioned is stratospheric cooling. I'm not sure the evidence is so convincing there. And the other one is changes in radiation balance, which hasn't really been measured. So the real question is how do, you know, these are relatively small changes, 0.8 of a degree C. And again, I really object to this idea of using this global average surface temperature. Let's look at where the real effect is, which is in the polar regions. So how do you distinguish these changes from other things going on? They're what they call feedbacks. All sorts of, are they positive or negative? Is it worse than the models say or better? Let's think of one thing. If I were to change the cloud cover by 1%, just 1%, that would give a forcing equivalent to that attributed to CO2. One of the assumptions that people have is that there was an equilibrium climate back years ago, that people were happily dancing around the maypole in the Middle Ages and nothing changed. We know that's not true. We know that short-term fluctuations, what people call weather, is chaotic. It's why you can't predict the weather more than about 10 days in advance. But is climate chaotic? Can one prove mathematically that if you average over a certain period, you lose chaotic behavior? Can climate even be predicted? I'm not sure. I mean, well, there's one documented example. There's this Joseph predicted at least the climate in some part of Egypt 14 years out. And although by all accounts, he's kind of full of himself, at least he attributed that to divine inspiration. So I come back to what Feynman said. Scientific knowledge is a body of statements of varying degrees of certainty. Some are true, some are nearly true, none are absolutely certain. How much do we really know? Well, there's a lot of uncertainty out there, as Ariel Anbar said. But what is science? It's a way to tell you how to learn things, to what things are known, and how to handle doubt and uncertainty, and what the rules of evidence are. And one thing I want people to take away from my talk is when people talk about science and climate change or anything else, I want people to make a clear distinction between what is a hypothesis, what is the result of a model, and what is an actual observation. But there's another side to the ledger, another side to the coin. You know, we heard all about the evils of burning fossil fuels. But let's be honest, we all derive a lot of benefits from burning fossil fuels. What are we going to give up? It's not just the toilet paper in the store. You know, one could say that it was the burning of fossil fuels that ended servitude and slavery. If you want the most eco-friendly form of transportation, it was the slave ship. You know, another thing we hear is that it all started at the start of the Industrial Revolution, but that's not what the temperature record says. I mean, we're going to have a start date. Why not when the first humanoid rubbed some sticks together and started a fire? And where did this 1.5 or 2 degrees C threshold from the IPCC come from? And what is it based? I mean, let's be honest, you know, this is less than the temperature change between 8 and 9 in the morning. So the real question is, what are we going to do about it? Maybe we can just live with it. That's called adaptation. It's something that we have to seriously consider. But the last point I really want to make is that if we are going to do something about it, it better actually work. This is from my book. This shows the CO2 emissions per person per year in tons of CO2, metric tons, for United States, Germany, and France. United States starts very high at 20 tons per person. It's now dropped to just over 15, actually. It's about 16, 15 tons. That, the environmentalists are not going to be very happy to hear why that happened. That's because of fracking. What fracking did is made natural gas so cheap that utilities of their own accord substituted highly efficient combined cycle natural gas plants for coal. This is, middle one is Germany. This covers the period of what they call the Energiewende, the energy transition. Germany now has more solar and wind generating capacity than coal or natural gas. What change has it made in CO2 emissions? Well, I'd say looking at that graph, the answer is none. Maybe things changed since I wrote the book, so I redid the data for as long as I could after that in the fall. And no change then either. But look at France. France and Germany are very comparable in standard of living, and what drives CO2 emissions and energy use are two things: standard of living, but you know, after a certain point, you kind of go into saturation. You really don't use any more energy. But the other big thing is actually the local climate. Cold places are very bad, nice tropical islands are great. So France and Germany are very comparable in those senses. There's similar energy use for transportation. And notice how much lower France is than Germany. That's because of the French baseload is all nuclear. So there's something that actually works: substituting coal by nukes. So let's say we want to cut CO2 emissions globally. It's about 35 gigatons a year. It's quite realistic to think of getting rid of coal. That's the worst thing, having coal. And you'll cut out about 12 to 13 gigatons. That's almost half. That's a realistic objective. Net zero isn't. But whatever we choose to do, as I say, actually has to work. And we've got to remember that not all fossil fuels are created equal. Coal is really bad. Natural gas is great because you can use it in combined cycle and you get more energy per CO2 molecule. But not all renewables are created equal. Large-scale hydro has the advantage you can use it for baseload, for peak load, but best of all, you have interseasonal storage. Wind is totally intermittent. Basically, you get your wind in a weather system. That doesn't happen, no wind power. Solar, it can be reliable in places like Phoenix with 300 days of sunshine a year, but it really does a bad job of matching demand. So then we're talking about Germany, and Professor Gottlieb talked about the mindset in the Holocaust, and I don't see that their mindset with their renewable obsession is really any different. It's, you know, we're putting up all these wind turbines and plastering roofs with solar panels, but for why? I mean, if it's not changing CO2 emissions, what is it doing? Well, maybe it's a religious act. You know, it's like building cathedrals or totem poles or whatever. Or to paraphrase the psalmist, "Atzbechem silicon v'neodymium ma'aseh yedei adam." And then there's the whole trading, the carbon trading, emissions trading. ASU is big on this. You know, really, it's a form of sin offering, isn't it? It's you know, I want to have all the good things in life, but I will atone for my sin. And this idea of, you know, the having the good things in life, there's something bad about it, asceticism. This isn't part of Judaism. I mean, it's more of medieval Christianity than our tradition. I suppose the sin offerings reached their peak in the Middle Ages of the Catholic Church and the trade in indulgences, which Martin Luther took exception to. But what all this talk has done is it's created a very fertile environment for a whole bunch of hucksters and charlatans who are proposing to live in a techno-fantasy land. Yes, this is the battery cell used in your Tesla. By the way, a Tesla, to build it takes 5 times the energy that would be needed to build a comparable gasoline-powered car. It's called a 2170. It's about the size of a AA battery. Yes, we see these pictures of this truck being propelled by these batteries. Well, do the calculation. You'll find that there's very little space left for the payload in the truck. The batteries, the truck, a normal semi has a payload of 15 tons. The batteries weigh about 8 to 10 tons. And then you see these eVTOL air taxis. Well, they're not really going to get off the ground. Well, maybe they will, but they'll fall back in about 2 minutes. And even more absurd, filling containers with these 2170s or equivalents for grid storage. Yeah, as they did in Hornsdale wind farm in South Australia. That buffers your load for 20 minutes when you need 10 days. This is why I call it techno-fantasy land. So I'd like to summarize by saying, is there a climate crisis in the same sense we have a pandemic crisis? No, I don't think so. Is it a cause for concern? Yeah, we should worry about it. And but what I will say is that anything we do actually has to work. Thank you.
Thank you very much. And I thank all of our panelists for a very, very interesting discussion thus far. I think that there's probably a number of questions that can come. We will be opening up for questions from the Q&A function on Zoom. So if you have questions for either one specific panelist or all three, please put them there. I'd like to actually start us off with a question that I have been thinking about with all three of these presentations. And it's definitely coming from, I come from religious studies, and so you will have to forgive the fact that I'm immediately going to take a lot of the scientific information and immediately translate it into my home discipline. It seems like each of these presentations have looked at planetary habitability in ways that really not only depend on the concrete manifestations of what habitability might be for the human species, but also just as importantly, about what human flourishing and advanced civilization might actually entail. And so we've heard about our need for communications and the fact that being alone is something that we feel in a very particular way. We've heard about energy use needs in a practical way, and also in how energy use is important for our self-understanding. We've heard a lot about uncertainty and how our need or desire for certainty and knowledge plays an important role in our politics, our economics, and our self-definition. And finally, the fact that our interpretation of the world of who we are as individuals, as a species, and creation overall really depends on a lot of these different dimensions that we've heard about. So I was wondering if each of the three panelists could offer a little bit of reflection about how the scientific work that they're undertaking helps us to understand habitability and human flourishing, and whether that question of habitability is mainly a scientific question or mainly a spiritual one. And I welcome any of the three of you to take a whack at that. I'm certain that that's yeah, at any rate.
I mean, I'll start taking a whack at that, right? So I'm a geoscientist and an astrobiologist. So I study Earth's history, its deep time history, and the evolution of life on Earth over time, and its intersection with evolution of the environment, and then try to in much of my scholarship, try to understand what the relevance of that is for searching for life elsewhere. And so I end up taking a very long view, even among natural scientists, a very long view of the planet and our place in it. Which on the one hand, leads me to conclude that this sort of self-aware tool-using intelligence really is a pretty exceptional thing in the history of the planet. And although we have this tendency to want to say, well, we're just animals like all others, no, there is something pretty distinctive about what we're doing, and I think our impact on the environment is a consequence of that. But then I also do look at this sort of, to some extent, what we're doing seems to me to be inevitable, in the sense that the history of life is a history of innovations, of evolution leading to innovations in what life can do, and then organisms then exploit those innovations to benefit themselves one way or another, right? And then you have survival of the fittest. You have conflict between different organisms, different species, until they reach some kind of modus vivendi, right? So so when I look at that with the historical sweep, it's hard for me to imagine that we would evolve the capability to do the things we do and not do it. So then the question is, are we smart enough? Unlike cyanobacteria, which figured out how to make oxygen, which was devastating for the biosphere before that, right? But created a path for our biosphere. But they had no brains, right? They couldn't. They were unaware of what they were doing. We are aware of what we're doing. We are aware of what it's doing to the biosphere that we evolved from. So do we, choose over time and evolutionary time as we go forward in the future to guide that or not, right? That's the unique thing about us. So I'm not sure this is exactly answering your question, but where it leaves me is that it is profoundly, the future is profoundly a spiritual, the future, our future on this planet, and hence the future of this planet, given the power that we now have, is profoundly bound up in spiritual questions, because it has to do with what we as human beings have this unique ability to be self-aware and reflective and shape our actions, choose to do with that.
So I would echo that comment. What our study of exoplanets that we've been able to study teaches us what planets are like and what makes a planet habitable. Of course, we have no evidence that there's life on any of them. We only can test ideas to see whether liquid water might exist. Perhaps their atmospheres have oxygen and so forth. But the reason it's so important, the reason I think it's so important, is because our attitude is really what matters. Do we think that we are insignificant? Do we think that aliens exist throughout the universe, and maybe Oumuamua just was a nearby civilization that dropped by, and so we can just go to another planet when we ruin this one, or if things die off, not to worry, right? We just go faster than light to someplace else. That's what's so dangerous, because if you recognize that we are special, that we are rare, and that we're not going to know for eons, probably, whether there's any other civilization, then the attitude that we bring towards things that we value changes. We're not a dime a dozen. And so then you have to say, well, when I wonder what is it worth to care, then you have to understand that we have no options. That this is not just our planet, but we might be the only civilized life for all we are going to know. In the whole Milky Way, surely we must go to extraordinary lengths to protect it.
I suppose I should chip in my 2 cents worth. I'd like to expand on Ariel's point of the era of the Anthropocene. We should look at it as we're living on a spaceship, and we have to manage that spaceship just as if we were sitting in an Apollo capsule. You've got to pay attention to your CO2 levels, your oxygen levels, power levels, all these things. And imagine that what's going on is it's kind of like, Apollo 13. So, but that being said, one shouldn't use alarmist projections. I mean, something I should have said in my talk is I hear all this talk of climate change, and do you know what it reminds me of? It's when that part in Bechukotai, when you have to race through it because it's all so bad, all the horrible things that are going to happen. And then there's also, it's repeated for good measure in Kitavo, in case you, Parshat Kitavo, in case you weren't scared the first time. And so, there are always going to be compromises between getting benefits from burning things and any consequences thereof. And so everything is a matter of weighing the benefits against the costs.
So thank you to all three of you. We have a few questions that I'd like to pose coming from the question and answers function. The first comes from Paul Fieldstone. And he asks about the role of advanced small modular nuclear reactors and whether we should be using natural gas as a bridging fuel, focusing more on that kind of innovation and seeing what that might mean for a pragmatic, realistic future. And this question was initially directed to Ariel, but I think also Peter had mentioned a little bit about energy policy, and so he might be able to answer that as well.
I'll defer to Peter to talk first. He's certainly studied that more than I have, and I actually think I agree with him on nuclear. So,
yeah, small modular reactors are a great idea. I mean, ultimately, all our problems are solved with controlled nuclear fusion. You do the calculation like I did in my book. If you have controlled nuclear fusion, rather than using the lithium in the world for batteries, you use it in a DT reaction, you have enough energy to go for the whole life of the solar system at present levels of energy consumption. You're good to go. The beauty of nuclear is you get a lot of energy from very little stuff. And the problems with waste are greatly exaggerated. The main thing in waste is the cesium-137, and that has a half-life of 30 years. So by about 5,000 years, it's down to background level. And I know people say, well, how can we store stuff for 5,000 years? No structure that humans have made has lasted 5,000 years. But let me just say that my ancestors constructed some things in Egypt 5,000 years ago, they're still there. And as my wife keeps telling me, my family are lousy at construction. So, it's part of the solution set. It very much is. And what the advantage of the SMR is that it lowers costs, and you just send it out wherever you need it. And when it's done, you just bring it back. And so it solves a lot of the problems. I don't see natural gas as a bridging fuel. I think it's always going to be needed because nukes will not meet what are called peak loads. But if you electrify ground transportation, like everybody goes around in an autonomous electrically powered Uber, that actually makes things more baseload-like. So that also helps as well. There are a lot of things where you might be going in the right direction for totally different reasons, not because you care about the environment.
Thank you. This question, oh, I'm sorry, Ariel, did you want to respond?
Well, I could just riff off of that a little bit if you want, or we could go to a question.
Please do.
Yeah.
This been about for other reasons. I think it's this energy transition question gets strongly rooted in climate change and the environment. I think there's a whole other framing that we could be, and that Jews could in an interesting way be talking about with regards to energy, which is that, if you look at that energy projection curve that I gave, which I granted, again, taking any exponential projection with a grain of salt. But clearly the demand for energy on this planet is not going to decrease. There are billions of people who want to live at the same standard that we live and have every right to demand that. And there's no way to do that without increasing the use of energy. And so, if you look at fossil fuel just reserves, and there's always fossil fuels are always on the verge of running out, but at some point they will run out or they become prohibitively expensive to obtain, and other things become more effective. You can make good arguments that if you're thinking in 50 to 100-year timelines, we're having to plan for that now. And considering that when we build power plants and do these kind of infrastructure investments, we're usually thinking on 50, 100-year timelines, this is a time to be thinking really seriously about the energy demand at the end of the century, which is going to be far greater than it is now. And there's opportunity there are markets there's money to be made by figuring out how to meet that demand, right? And so I think for reasons totally divorced from climate, we could be and should be pushing to shift the energy base away from fossil fuels. And we could be tapping, people's greed and avarice, wanting to make money off of that future that's coming, right? To drive this. So for all the wrong reasons, depending on your moral frame, we could be pushing in the right direction. Again, if you believe that getting off of fossil fuels is a critical thing to do, or at least minimizing their use.
I want to react briefly to that also, just to say that I don't think unlimited energy use, even nuclear, is good. There are thermodynamic consequences. I think we have to reduce our use of all energy. Of course, we want it to be the best possible energy, and I think there is a role for nuclear energy for sure. But to say that with a fusion generator, our problems go away, they don't go away. They don't go away. Neither is unlimited population. The Earth can't sustain it, and there's no place else for us to go. So we should not. We should prioritize a restricted use of energy. We just use too much of it. Can't keep it up. Not everybody will be able to enjoy the standard of living that we live now.
So
What are you going to individually up?
So I think the sign of a really good session is that unfortunately we've run out of time and we have far too many questions to go over. So first I'd like to thank everyone who put in questions, and I apologize that we weren't able to do that as a group, but hopefully they'll be able to be answered independently through the Q&A function. And I'd also like to once again thank all three of our panelists for an absolutely wonderful conversation, a great continuation from what we heard from Roger Gottlieb a little bit earlier. So thank you to the three of you.